Hello, everybody. Mr. Klein here. Still wearing a hat because it's still fun. And right now we're going to talk about exponential calculus, which means the calculus or the rates with exponential functions. And so I picked a nice, easy exponential function. In fact, let me tell you, folks, if you like easy lessons, and if I've noticed something about this year's class is that you do, this is going to be the easiest lesson that you've ever seen. All right, so here's an exponential function, and hopefully you can picture what the graph looks like. But let's plot some points that are on it. If we plugged in 0, we'd get 1, and if we plugged in 1, we'd get 2, and if we plugged in 2, we'd get 4. If we plugged in -1, we'd get a half, and if we plugged in -2, we'd get a quarter. And the exponential function looks something like this. Our goal is to cook up the derivative function. And let's just start by hitting some slopes. So I'm going to hit the slope at 2 and at -1 and at 0 and at 1 and at 2. So let's look at those 1, 2, 3, 4, 5 slopes. The first thing that I notice is that every single one of those slopes is positive. That really sounds like a dog. I don't even have a dog. Yeah, all of those slopes are positive, which means that the derivative equation is going to be positive. The other thing that's really worth noting here is that as we move from this one, which looks like it's close to 0, we move to this one, which is a little bit larger, and then even larger, and then larger, and now they really look like they're starting to take off a little bit. So the graph that we're trying to cook up of the derivative function, it's going to be increasing. Why? Because the blue slopes are increasing. And also, what does it look like? It looks like another exponential function. So put your pen down for a minute, and I'm going to show you something. I took this function, went ahead, and I put it into my calculator right here. And then I used nderiv to graph the derivative function here. And so if I hit table, it'll give me at 0. Here's the value of the function. Here's the value of the slopes. At 1, here's the value of the function. Here's the value of the slopes. And at 2, here's the function. Here's the value of the slopes. Now, something interesting happens if you take the slopes, so what's in y2, and you divide it by what's in y1, and you look at the ratio. This is something that is special to exponential functions. So check this out. I'm going to come on down to y3 here, and I'm going to say, let's take the rate, which is in y2, and let's divide it by the function, which is in y1. And then let's look at the table. Notice that for 0, the ratio is 0.693. For 1, the ratio is 0.693. And for 2, the ratio is 0.693. In fact, it doesn't matter what number we pick. Pick any of your favorite numbers. That ratio is constant. Well, let's think about what this means. Back to our paper. If the ratio is constant, then taking the rate function, the thing we're trying to find, and dividing it by the original function gives us a constant value, and let's remember what that was. It was 0.693. And what that means, I'm going to do just a little bit of algebra here. is that if we take both sides of this proportion and multiply by f of x, we get that the rate function, the thing we're trying to cook up, is equal to 0.693 multiplied by the original function. Hey, and what was the original function? What was that? It was 2 to the x. So that means that our derivative is this constant multiplied by 2 to the x. And it turns out that this is always the case, everybody. If you start with something like 2 to the x, the derivative will be something times 2 to the x. Likewise, if we had changed this to, I don't know, a 3, then we would still have just some constant multiplying in front of us. And you don't want to have to put this in your calculator and do all this rigmarole every time you want to figure out this number. So there must be a shortcut. There is. And I'll give you a hint. It is easy. It is so easy to come up with the number that goes right here. Can you guess how we get this number in a way that is easy? All right, here it is. Remember the natural log? Natural log is a log with a base of e. Well, if I hit, not that button, natural log of our base was 2, I get 0.693. So what this really is right here is the natural log of 2. Which brings us, ladies and gentlemen, to what I am going to call the exponential rule. And the exponential rule says this. If a function is defined as a base, a number, to the x power, so again, you're only going to use this when you have x in the exponent power, because that's what tells you you're dealing with something that is exponential. Then the derivative function will always be the same thing that you started with multiplied by a constant. And that constant is the natural log of the base. I really want to emphasize that last piece of what I said right there, that this right here is a constant coefficient. It's a number. So there it is, folks. There's the exponential rule. You can add that to your library of rules that you know, along with the power rule and the chain rule and those trig rules. Okay. Let's work some examples. We're going to do a bunch of them today. First one. Remember what this notation means. This means you want to take the derivative of the function that is inside. You say to yourself, is this an exponential function? Answer, yes. Therefore, the derivative will simply be the natural log of the base multiplied by the original function. There's your answer, and you're done. All right, let's keep rolling. Number 2. Suppose that our function is 3 times x to the 7th power plus 3 times 7 to the x power. and we want to cook up the derivative expression. Well, I've written it this way for a reason. I want to start with this first expression, which is the kind that you are familiar with, right? This is a power function because the x is in the base. And so we could use the power rule here. Of course, when we do the power rule, we take the 7 and we bring it down and we multiply it by the 3. That 3 is what I'm going to call a constant coefficient. So when we multiply this out, we're going to end up with the 7 comes down, we still have a 3 times 7x to the drop the power by 1, and you get 6. Well, look at the next part. Right here we have a constant coefficient 2. So when we evaluate the second term, we're going to play the exact same game that we played here, where we're just going to let that 3 hang out. Everyone likes hanging out. In fact, I'm going to write that down. Constant coefficients just hang out. They don't do anything but sit right where they were. So that would mean we still have a 3, and we say, what's the derivative of 7 to the x? Well, according to the exponential rule, that would be natural log of 7 multiplied by 7 to the x power. If you wanted to clean this up, you could combine the 3 and the 7 and call those a 21. But over here, there's nothing you can do. You just got to say it's 3 times the natural log of 7, 7 to the x. And there is your answer. Example 3. If y is equal to, give me one of your favorite numbers. What was that? 5, all right. 5 to the x. I want you to find this. Now, I apologize that I haven't spent very much time talking about this notation. Call that when you see d squared y, that means it wants the second derivative. So this is going to be a two-step problem. First step is to take the derivative of y equals 5 to the x. Was this an exponential function? You bet it is. So the result will be the natural log of the base multiplied by the original function. Step 2, let's now take the derivative of the derivative. When we do that, you got to think a little bit about this guy right here. This is a number. And that means that it is a constant coefficient. Look back at the last example that we did. On that last example, so disorganized. Oh, here you are. When we had a constant coefficient, the 3, it just hung out. So here, as we go to the next step, we're just going to take this natural log of 5 and let it hang out. Bring it on down. So that'll give us a natural log 5. And then next door to it here, I'm now going to take the derivative of 5 to the x, which is natural log of 5 times 5 to the x. When I roll my hand away, we see that we have not 1, but 2 natural logs of 5. And the appropriate way to write that expression would be like so. the natural log of 5 is squared because you're multiplying it twice, times 5 to the x power. Here's an interesting one. I'll tell you what, give me another number. 6, all right. F of x is equal to 6 to the x. Then I want you to tell me what this is equal to. See that 15 there? Can you guess what that means? See a 15 in parentheses? That means take the 15th derivative. Now, if you're thinking to yourself, Klein, you tripping. I'm not going to do that. I'm not taking 15 derivatives. I don't want you to. I want you to think smart. I want you to see if there's a pattern up here that would allow you to do this problem very quickly. And there is. You know, when we wanted the second derivative of this exponential function, here we ended up with the same thing that we started with. Right? We had a 5 to the x and a 5 to the x. So I'm pretty confident that down here we're going to have something times 6 to the x. Now, what should go in that location? Second derivative, second power. Therefore, 15th derivative, we're going to get the natural log of 6 to the 15th. This brings us to the moment we've all been waiting for. There are moments in your education where things kind of all come together, and this is one of them. I'm actually being serious. I want to look at this. E to the x. Remember when you first heard about e to the x? You were sitting in Algebra 2, it was a couple years ago, and your teacher told you that e was a base, and you said, what's this trash, right? Here's the answer to that question. Here's the reason that we talk about e like it's a number, that we care about it. If f of x is e to the x, then its derivative would be something times e to the x. And what would that something be, everybody? Well, the natural log of the base. So the natural log of e. But what is the natural log of e? Isn't it just 1? Well, if this is just 1, that means that the derivative is just equal to e to the x. So look at this. This only happens once. The derivative of e to the x is just e to the x. Or in other words, the derivative of e to the x is itself. Its rate is equal to its value. Function equals derivative. F of x equals f prime of x. Now, how is that going to help us? Well, doesn't that make things a lot simpler? For instance, let's suppose I threw this problem at you. Let's say we're looking at take the derivative of e to the 5x. Now we can see that this is a chain rule problem, right? You've got an outside function. That outside function is e to the power. But then we've also got this inside function, and the inside function is 5x. Now I've noticed that sometimes students have a hard time identifying where the inside and the outside function are when we get to these exponential ones. Here's an easy trick. Easy trick. Just pick a number, any number, like 4. Imagine that we plug 4 in right here. Isn't the first thing that we would do with that 4 to take it and multiply it by the 5? Well, if the first thing we do is multiply by 5, that tells you the inside. The first step is the inside. So our inside is take 5 and multiply it by your number. Okay? So anyway, we know that when we do chain rule, there will be a couple links in the chain, so something like this. And the reason that e makes this easier is that if our outer function is e to the power, what we just learned up here is that the derivative of e to the power is e to the power. So nothing's going to change here. We're going to say e to the power. The power is the inside function. We know that always gets left alone. So anytime you'll do one of these, the exponent will stay the same. But then here we need to multiply by the derivative of the inside. And the inside, 5x, would have a derivative of 5. You want to write your final answer as 5e to the 5x. All right, one more for today. Let's suppose you ran into something that looked like this. S of t is equal to the cosine of e to the t squared. And you want to come up with the derivative. I'm doing this one because this is a 3-stepper. Look, our innermost function would be to square the t. Our middle function would be e to the power. And then our outermost function would be the cosine of something. So I'm going to write something times something times something. And we start with the cosine. Well, the derivative of cosine is negative sine of something. That something is e to, that really just sounds like there's a dog around here. I don't even have a dog. E to the t squared. Multiplied by, move to the middle function. Now our middle function was e to the something. We know from our work right here that the derivative of e to the something is e to the something. So this will be e to the something multiplied by the derivative of the innermost function, which is t squared. That would give us a 2t. Final answer, take the negative and the 2 and start by pulling them up front. So coefficients always go first. Second will be the power function. Third will be the exponential function. And then always leave your trigs last. Sine of e to the t squared. You can't do anything with these e to the t squareds because one's inside the sign. So there would be your derivative. And there it is, folks. We learned a couple of very useful things about exponential functions, and now we can take their derivative.